Our starting premise today is called falling from the sky. And so what's happening here is there's a 500-foot tall building, and we're throwing the rock from the top. Okay?
That would kill someone.
Yeah, that would.
Not the rock. Okay?
The rock would.
And so there's a camera capturing the rock on the way down. And it gives us 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. What you need to do is say, how far will the rock have fallen after 6 seconds? Then you're going to look at some stuff that Jada noticed and answer the questions for question 2. Question 2 on the student packet is going to be the next page, so just know you're going to have to do a flip. Don't just do the page and stop. You're going to complete everything up here with your table partner or whole table if you're a group of 3. So I walked around, and I don't know if I actually saw the right answer to this, although I saw a lot of good things happening for number 1. The answer 2, how far will the rock fall, is 500 feet.
Oh my.
Okay, so let's listen to why.
What the heck? I actually got it. No cap.
Let's talk about why. The building's 500 feet tall. And you may have noticed that the difference from 4 to 5 seconds has to be more than 144 because the difference is increasing. So if there's only 100 feet left, and I know it's going to fall more than 144 feet, it'll stop at 500 feet. Let's look at what Jada has going, because this is where we really build concept of what's happening. Some of us found in a pattern and extended it. This is where we're going to make the connection from the things that we've been doing to this. So far, we have looked at images, right, and patterns, and we have seen how they've changed. What was the independent variable every time for that?
Honestly,
From the pictures. There are no seconds with pictures. From the pictures.
Blocks.
For the blocks, what was the independent variable? For the blocks in all the pictures? And the dots?
the step number.
The step number, right? That was always our independent. Now, what is our independent variable? Seconds. So we're going to make a connection here. When we were dealing with the steps, what were we always looking for? A square, right? We're always looking for a square. Why are we looking for squares, guys? It's quadratics, right? There is something square. That's why it's quadratic. So now that we don't have an image, we're still looking for the square, okay? So that's what Jada's doing. Jada wrote down all this stuff. She said she found these factors of 16. Everything had a common factor of 16. And then she saw this other number. So after 1 second, there was 1. We'll write that, 1 second. After 2 seconds, there was 4. After 3 seconds, there was 9. After 4 seconds, there was 16. And after 5 seconds, there was 25. So she wants now, like any good experiment, you threw the rock off. She's like looking for 6 seconds. It didn't happen. So then, when you finish a good experiment, you should want to be like, hey, if there was a taller building, how long would it take for the rock to hit the ground? Or at 6 seconds or at 7 seconds, right? You ask questions. So now we're going to deal with the theoretically as tall as we need the building. And she wants to know 7 seconds. So instead of doing 16 times 5 squared, what I'm going to try? 16 times 7 squared. There's my square that's popping up again. And what is 16 times 7 squared? Anybody already do? 7 squared is 49.
Oh yeah, I just 784.
So 784. So Cam brings up a good point. One thing I like to do when I type this in a calculator is I'll just do 16 times 49. Like I don't need this. I know 7 squared. So this is how far the rock would fall in 700 or in 7 seconds. Okay. Now, just for fun, I want to look at these second differences with you. Okay. I told you we'd talk about those second differences again. I got to make a spot to write here. So for the second differences, at 0 seconds, how far did it fall?
0.
0. Thank you, Cam. Okay, after 1 second, it was 16. 2 seconds, 64. 3 seconds, 144. 4 seconds, 256. And 5, let's just do. So let's find the first difference here. First. Okay, 64 minus 16, 48. 144 minus 64, 80. 256 minus 144, 112. 400 minus 256, 144. Guess what, guys? The second difference is 32. And remember earlier,
Oh, that's what I do.
yeah, from the warm-up, right? Let me tell you how I know the first difference is 22, okay? Or 32. By looking at the function. The function is 16t squared, correct? Did everybody grab? If I square the time and times 16, that worked every time. Just like the pictures, I have my square and then the thing that's happening to all the squares. Now here's how I know by looking at this. All the other stuff we looked at was like x squared. And that had a common difference of 2. That's because the coefficient 1 in front times 2 gave me a second difference of 2. If I take this one has a leading coefficient 16 times greater than that. So 16 times greater than a second difference of 2 is? 32. That's why on our warm-up, when we saw 6x squared, I said the second difference is 12. And if we were to see something like 6x, or I just did 6x squared. Let's say 30x squared, the second difference would be 60. And you can use that to do like a lot of problem solving, a lot of checking your answer. The second difference doesn't do a lot for like getting answers, but if you have like a table and you want to know if it's quadratic, you can do a second difference, and then you could use that to get a leading coefficient, or you can just check things on a table using it, right? It's a great check. It's a great thing to understand for that. This function, you're going to see 16t squared all over the place, especially when you get to physics, because it deals with gravity. That's why I said it's one of like my favorite ones, because it's a real thing that deals with gravity. Yeah, Meredith.
So if
Let's set up our last problem for today. So the guy that discovered this gravity stuff is Galilei. You know he's good because they reference him in a Queen song. And he comes up with this function. The distance falling equals 16 times t squared. This is the function we saw in the warm-up. We saw it with the rock that we pushed off the building, okay? Now, this works for any object. It's a theoretical thing if there's no like wind and stuff. So you're going to answer these questions with your table or table partner. How far is it going to fall in a half second? And then you're going to check out Elena and Diego's tables, see what's the same and what's different, and then complete their tables. Let's go. Here's something I like seeing for number 1. I like seeing this. A lot of folks had something like this. And that told us it would be 4 feet after a half second. All right, and I could tell what you did because people had written, we know 16 times time squared, right? 16 times time squared. If the time's a half second. I don't like to mess with decimals in my work a lot if I don't have to because they look like periods and multiplication. But who can tell me before we start filling out these tables what is the same about the tables? What is in common? Give me one thing, Ryan.
They both use the same amount of time.
Yeah, they have both in seconds, and the seconds increase by what? 1. And that's nice because then you can compare things well, right? Was it you, Ryan, too, that told me something else was in common even though it doesn't look in common?
The distance from the ground and the distance fallen, they're the same thing.
Yeah, so these are both how far something is about something that's falling. They're both about something that's falling, even though if it doesn't look like it, right? So the next thing to think about is why is one decreasing while one is increasing? So who can tell me that difference? Why is there that difference? Riley?
well, what is the difference from the ground versus
Yeah.
like how high?
One is like, yeah, how far it has fallen or how far does it have left to fall, kind of, right? And we've seen this with some other functions in the function unit this year, too. So let's fill out this table. I like to go straight to the function first. We know 16t squared will tell us how far something is fallen because Mr. Galileo. And if I start plugging in answers, which we've already seen this function, right? 9 times 16 is 144. And 16 times 16 is 256. We've seen this. We've already seen this xy like over and over today, right? Now this one's going to be different, and I like to jump right to the function first. Who can give me Diego's function? It's related. So like one thing to think about is if I know how far it fell, how do I figure out how much is left, Josiah?
576 minus 16 times t.
Yeah.
You
So
just do 576 minus d.
I get what you're saying, but it's in terms of t here. But yes, the distance. So I'm going to start at 576, and this is a classic example how the function talks about what the situation is like. I can read my function situationally. It's starting at 576, and I'm taking away how far it's fallen already. So, for 3 seconds, I know at 3 seconds it dropped to 144. So 576 minus 144 gives me 432. And at 4 seconds, I know it dropped 256. So 576 minus 256 tells me 320 left. And that number should be decreasing until it hits the ground. Or, for practical purposes, there's a thing called terminal velocity where nothing will go faster because of air friction. But look forward to more of that in physics in a couple of years. So we're doing physics today, whether you know it or not, with gravity. It's kind of fun. So let's make sure we hit our learning targets. So, can we explain quadratic expressions and falling objects? Yeah, what's gravity? 16t squared. And fun fact, if our leading coefficient is 16, our second difference is 32. And we can use tables, graphs, and equations, multiple representations, even a picture of a building today. And we're moving from the sequences of little blocks. What did we look for there? We looked for squares. What did we look for in our numbers today? Squares. Because quadratics have a square.